In this project, we try to adopt the MPC from an existing project in MIT, which is for the quadrupedal robot, to build our own optimal control method for the bipedal robot. The idea is instead of using center of mass trajectory, we use action-reaction forces to build an MPC with the integration of whole body control to create a flexible and fluent robot movement to make it stand and walk like real humans.
Inspired by the MIT paper, we consider the whole robot as a particle in center of mass. For each foot, we consider the plane as the quadrilateral with contact at each corner. So it's totally 8 contact points for our mass module. There are mainly 3 assumptions for our dynamics. The first assumption is that the roll and pitch angles are small enough to ignore. In a state of walking and standing, only the yaw angle is significant due to the characteristics of bipedal robots. Since standing and walking is the low-speed module with little disturbance, the second assumption is that the states of bipedal robots has insignificant differences compared to the commanded trajectory. The third assumption we made is that all the non-diagonal elements are close to 0 in the inertia tensor matrix.
Using the above assumptions, we can simplify the system to rigid point masses centered at the robot center of mass. For the quadruped, there is a moment arm per leg that is fed into the MPC from the state estimator. Then, shown in red are the required reaction forces for each leg calculated by the MPC in order to achieve the desired trajectory for the center of mass. Using the above assumptions and models, the discrete system dynamics can be expressed as shown. The states in X are the angular and linear positions and velocities. And the cost function minimizes the trajectory error for the body center of mass as well as the control input forces for each leg. And finally, the constraints are placed on the inputs to maintain traction at all times.
According to the series above, we designed a simple MPC that could use information of the position, roll, pitch, yaw, velocity, angular velocity from estimator and sensor to calculate the contact force of the quadruped, and then using Jacobian to transfer those forces into torques and motors. To test our model, some experiments has been applied to the MPC. The objective of these experiments is to test whether our MPC can stabilize the robot under some disturbance. As is shown in the figure 1, we intentionally let the roll of COM increase with time, and in figure 3, we add some disturbance in input XY position of COM. As is shown in the following figure, our MPC shows excellent resistance and disturbances. The deviation from origin is within an acceptable range, and also we can see in the figure 9, the FZ of leg 2 and 4 are bigger than the FZ of leg 1 and 3. Which indicates that MPC is adjusting the input roll shown in the figure 1. So in conclusion, this experiment shows that the design of our MPC is correct and reliable. It could perfectly withstand some slight disturbance. And in that case, we can move on to the simulation.
From the simulation, we can see that the robot can keep its balance for a rather long time. However, it can only bear slight disturbance. Note that during the simulation, the video stuck very seriously. It's because it has too much time complexity. The fact proves that Pyomo is not suitable for solving real-time PC problems.
While Pyomo is good for quickly setting up an experiment, its runtime is too slow. That is why for controlling the bipedal robot we used OSQP. It's a much faster solver. Adapting our quadruped MPC design to fit the biped, it is now solving 4 reaction forces per foot and 8 outputs total.
In the future, better optimal control can be adopted, such as smaller test times to reduce the discrepancy. Also, a high-fidelity model can be adopted to get more rapid learning speed and fewer training steps. And that is our project. Thank you.